This week we are looking at analysis of variance, and this is often shortened to ANOVA, and there's a lot of variations of it that you might see, ANOVA, MANOVA, ANCOVA, and they all based on the same sort of family of techniques. Now ANOVA will work for 2 or more groups, so you might be wondering, can't I just use this instead of the t-test, which we did last week? And yes, you could. The t-test is a very common test. It's a handy one to learn first up, and also it forms a part of some of the bigger techniques, so it's a nice one to start with. If we quickly look at the t-test, I didn't show you the formula last week, although you would have seen it in your previous studies. It is literally comparing the means. You subtract one mean from the other, and then you do some stuff with your standard deviations. So the question you might have is, how would you extend this to more than 2 groups? We can't just subtract another mean from it. How do we make that comparison if we can't do this simple subtraction here? And this is why we end up using the variances, even though we're trying to test the means. And I'll try to explain how this works. So let's assume that we have 3 samples all from the same population. So the variation in this first sample goes from about 120 to 180, same for the second, same for the third. So that means overall, when we pull all our samples together, the variation overall is very similar to what we get from any one of them individually, which is suggesting that they've all come, in fact, from the same population. Now, if we have a different situation, that's my arrows showing how they're all similar. If we have a different situation where these samples have in fact come from different populations and we pool them, we see that the variation in any one sample might be quite small, but because they're spaced along this number line with different means, it's actually pushing the variation out when we pool them all together. So what analysis of variance is doing is it's looking at comparing the individual variation from the separate samples with the overall variation with them all pooled together. And if the overall variation is a lot bigger than any of the samples' variation by itself, then that's suggesting that the samples are actually separated by some space along this continuum here, which is pushing this overall variation out. So it's suggesting that the means are different, even. And hopefully you can tell that an assumption of this test is that we do have similar levels of variation in each of the groups. Otherwise, this overall variation could just be coming from one particular group being very spread out. So when we want to use analysis of variance to check the means, the process is very similar to the t-test. We check all our assumptions. There are 2 versions of it depending on this last assumption of equal variances. And if there's a lot of problems with the data, we can switch to a non-parametric test. In this case, it's called the Kruskal Wallis test. But I will say that the analysis of variance is pretty robust. It holds up fairly well, even if your data is not perfect. So the first 3 are about how whether or not you've got the right data and how well your experiment is set up. So we should have a continuous outcome compared between 2 or more independent groups. All our observations should be independent. And then the last 3 are what we would actually check statistically, or with graphs anyway. There should be no significant outliers, approximately normal, and approximately equal variances. Now the data I'm going to use for this example has come from the Dryad data repository. It's from a paper called A 12-Week Exercise Program for Pregnant Women with Obesity to Improve Physical Activity Levels. I'm not going to look at the outcomes for this. I'm just going to look at some of the baseline data to see if our 3 levels of obesity are similar. So I'm going to have a look, is there a difference in the cardiorespiratory fitness, the VO2AT, of women in the different levels of obesity class 1, 2 and 3? And I've just put that in there just to remind myself what that VO2AT is from the paper, because I'm likely to forget. So assumptions 1 to 3, we have our outcome for this particular test is continuous, that's the oxygen uptake. We have independent categories. No woman can belong to more than one category. She's either in class 1, class 2 or class 3. I'm going to assume that the experiment was designed well and that we have independence of observations, and we would have to read the actual methods of the paper to to sort of validate this. We can't test that with SPSS. So assumption 4, are there any significant outliers? Well, there's a couple of outliers. I'm not going to say that they're significant. They're balanced either side, and also I happen to know we've got a really small sample in this group, and that can make box plots look a little bit funny if you've only got 7 observations or less sometimes in a group. So I don't think that's going to be a problem. Are they looking normal? Well, they're not looking completely normal, but again, we've got very small samples, so I'm going to say they're not very not normal. There's no particular problems I can see here with the normality. However, we can see a problem with the variances already. We've got a lot less variation in this group than we have in this, and we'll run the test for equality of variances as well to check. Now, this may just be due to the fact that they had such a small sample. Perhaps if they had a bigger sample, they would see more variation. So if we run this test for homogeneity of variances and we get a few versions of it, we can see that we do have some evidence that there is a difference in the variation between the 3 samples. So we're going to use the modified ANOVA, which is called Welch's ANOVA. And I think I can make my puppet point. So let's have a look at pointing. There we go. We're going to use Welch's ANOVA. I'll leave my hand up for a bit. And go back to the next slide. So when we're in SPSS, we just need to tick off a couple of extra boxes for our homogeneity of variances test and Welch's output for the adjustment for the unequal variances in case we need it. And we can get a means plot. I don't like this means plot though. We'll do our own means plots. So the null hypothesis is that there is no difference in the oxygen uptake between the 3 classes of women, and the alternative is that at least one of the means is different. I think I need to put my hand down now. The test itself doesn't tell us which of the means is different, and we have to do an extra step when we're using analysis of variance to check this. So in this case, this is your basic ANOVA, and then we have our Welch adjustment down here, and we're going to read this p-value. So we have very strong evidence from our sample that there is a difference in the mean oxygen uptake between the 3 classes of obese women in the population. So just remember that the purpose of inferential statistics is to get evidence from your sample to say something about your population. Now, the post-hoc comparisons are what is done to investigate which groups are different from each other. If you're Googling what on earth does post-hoc mean, just go for the second definition on Google, which means after the event. So after you have found that there is a difference, what is that difference? There's lots of different versions of this test. I don't think we need to know all the details of them. Usually you get similar results. Sometimes you get slightly different ones. Let's hope we always get the same ones. So in this case, for a basic ANOVA, we'll just use Tukey's test. Bonferroni is quite common as well. Excuse me. And then we're going to use the Games-Howe for the Welch's ANOVA. So what that looks like is we're just ticking a couple of extra boxes for our post-hoc multiple comparisons. And you can see you've got lots of options here. If you want to get right into the stats of it, then you might want to have a Google on what are the difference between all these post-hoc multiple comparisons. But these two will do for us. So what does it do? Well, we know there's a difference between at least 2 of the groups, and what it does is it goes through every pair and checks if there's a difference. So is there a difference between class 1 and class 2? No. Is there a difference between class 1 and class 3? Yes, there is. Is there a difference between class 2 and class 1? No. Is there a difference between class 2 and class 3? There's some evidence there that there's a difference. And we're going to take all of this with a grain of salt because we know that our sample size was so small for this study. But it looks like there is a difference in the oxygen uptake between the class 3 obese women and the class 1, and possibly also with the class 2. So far, we don't have any evidence that there's a difference in oxygen uptake between class 1 and class 2 obese women. Now, just for an example, we're going to have a look at what the Tukey's, that HSD stands for honestly significant differences, looks like. and the first bit is the same, and then it gives us this second bit of output, which are called homogeneous subsets. Basically what that's saying is it's going to put stuff in groups if they are similar. So it's saying class 3 and class 2 are similar, so they can go in a group, and class 2 and class 1 are similar, so they can go in a group. So you can belong to more than one group, but what we can see is class 3 is not in a group with class 1, so there's a significant difference there. Now, as a picture, I would always include one just to show what this looks like. And here we can see that the oxygen uptake is lower for the class 3, and if we're writing this in a paper, we'd give an estimate around how much lower it is compared with class 2 and class 1. If you're just trying to read this graph quickly before doing a test, if there's no overlap between the confidence intervals, you'll definitely get a significant result. If there's a little bit of overlap, you probably still get a significant result. Depends on a few things. If there's a lot of overlap, then you're unlikely to get a significant result. But you should always check with the test and not rely too much on the graph. Okay, so that's our basic analysis of variance. Now we're going to do a really quick example for the Kruskal Wallis test, and for this I'm going to have a look at the moderate to vigorous physical activity per day between the women of different levels of obesity. So assumptions 1 to 3 are similar to the previous example. We're after the outliers, normality and variances now. So we do have a couple of outliers, and if we were testing the means, well, one, this is going to cause a lot more variation in this group, but if we were going to just write out what the means are, it would be pulling the mean up for this group. So that could potentially be a problem, that we've got those outliers. If we do the histogram, I might not be so concerned about the normality because it doesn't look too bad. We have this truncation at 0 though, because no one can have less than 0 minutes of physical activity a day, although I'm fairly sure my teenagers try. But it is skewed, and this skewness is related to those outliers, and it could be causing a problem. And again, we do have this difference in the variation. So this might be a case where we say, okay, there's a few problems with our data, so we're going to use the non-parametric version and not assume that the data is normal. Similar to the t-test with the non-parametric version of ANOVA, we're testing, are the shapes the same and are the medians the same? So here we have no evidence that there's any difference in the distribution or the shape, and then if we run the test again looking for the medians, we've also got no evidence that there's any difference in the medians. So we've got no evidence that there's any difference in the moderate to vigorous physical activity between women of the 3 different levels of obesity from this sample. Doesn't mean that another sample wouldn't find something different. Now, if there was a difference, we could double click into those boxes to get some more information. I've actually just fiddled with the data a little bit to make this pop up, because you won't be able to get it if there's, you won't be able to get this view button if there's no difference. So you can see for the medians test, the overall means, you can see the group means, and they are different in this picture. Again, this is not their data, this is my fiddled data. And then if we want to get those pairwise comparisons, we click down here on the view. Hopefully I've got that up there. Oh no, my image is broken.